Today we are going to continue our discussion on hashing. In the last class we saw what a hash table was, what the concept of hashing is, and we also saw how to resolve collisions in hashing using linked lists. So that method of hashing is also called that method of collision resolution is also called chaining. So today we are going to look at two other methods for collision resolution, linear probing and double hashing, and we are also going to spend some more time discussing what hash functions, what good hash function should look like. So, what is a good hash function? A function which can be computed quickly, it should be quick to compute, and it should, as we said in the previous class, it should distribute the keys uniformly over the hash table. Right? It should not happen that all the keys get mapped to the same location, because then the performance of hashing would become as worse as that of a linked list. Good hash functions are very rare, and there is this famous paradox called the birthday paradox. Right? So there would be about 35 students here or 35 or more students sitting in this class, and there is a very high probability, and you can actually compute that probability, that two of you would have the same birthdays. Right? So although you would think that there are 365 days in the year, and if each one of you were to have one of these days as your birthday, then there is a very small probability that two would have the same. But that's not the case. Even with just 35 people, close to that, you would have a fairly high probability that two people would have the same birthdays. And the same kind of a thing is happening here, right? Your days of the year correspond to your slots in the hash table, and even if I were to take a key and put it randomly into one of those slots, there is a fairly high probability that two keys would end up in the same slot. That's the birthday paradox. So no matter what kind of a hash function you use, you're going to have collisions, right? There's no getting around that. And then there is also this notion, this problem of how to deal with non-integer keys. Right? In fact, we saw an example in the last class where the keys were telephone numbers, and we had written the telephone numbers in this manner. And how did we treat it as an integer? We just dropped this hyphen in between, and then we thought of it as an integer. We are going to see some more techniques of converting non-integer keys into integer ones. The other example that I had taken in the last class were your entry numbers, where again the key was a non-integer key because it had CSY or whatever, CSU or CSZ coming in there. Yeah. So we have to convert it into integers, and what we did in the last class was we said, okay, for those keys we are just going to take the last two digits as the hash function value. We are going to see some more techniques of converting non-integer keys into integer ones. So a hash function can actually be thought of as being in two parts. There is the hash code map and there is a compression map, and these two together make up a hash function. So recall, a hash function is basically a mapping of the keys to indices of your hash table. Your hash code map maps the key to an integer. If your key is already an integer, there is no need for this thing. Yeah? But when your keys are not integer keys, then you will have to first convert them into integer keys in this manner. Right? But this integer could be from an arbitrary range. Now we need to bring it to the range of to the size of our hash table. If n is the size of my hash table, then I need to bring this integer to the range 0 through n minus 1. Right? So that it can be mapped to an index of my table. So that part we will call it the compression map, and we will see what kind of functions are used, for these two things. One other important requirement of a hash function is that it should map. If one key gets mapped to a certain index, then the next time I want to map the key, it should get mapped to the same index location. It should not be that the next time it gets mapped to some other index location. You understand what I mean by this? So in the last class we took an example of a key which was, let's say, 2004 CS10110, and we mapped it to location 10, if you recall. Right? Now I cannot have a hash function which sometimes maps it to location 10 and sometimes maps it to location 13. Right? There could not be any kind of a randomization happening there. Why is that? Because when I inserted it, maybe I mapped it to location 10, but when I am trying to retrieve it, trying to search for it, if it gets mapped to location 13, then I do not know where the key is. Right? So it should map equal keys to the same indices. And of course, we have to try and minimize the probability of collisions. So let's look at what are the different, what are the popular hash code maps. Recall the hash code map is the part which converts your key to an integer. So one thing is that we could just take whatever is the bit pattern and interpret it as an integer, right? So that would be, if you have a numeric type with 32 bits or less, we can reinterpret the bits as an integer, as a number. Yeah. If you have, let's say, your key which has more than 32 bits in it, let's say it's some real number, a long or a double real number which takes more than 4 bytes, then you can add, you can take it in chunks of 32 bits and add them up. So take the first 4 bytes, add to it the next 4 bytes, and so on and on, to get eventually some 32 bits, and that could be the integer you are working with. So such a kind of a trick could also be used to compute the hash code map of a string. Suppose I was using the key as your name, right? So given a particular name, let's say Ankur, I want to compute the value of the, I want to convert it into an integer. So one possibility would be that I would, let's say, take the ASCII code of A, take the ASCII code of N, of K, of U, of R, add them up, right? And that is that I'll interpret it as an integer. Okay, you understand what I'm trying to say here? Now, why is this a bad strategy?
So two names cannot same be.
Why would the number of collisions be high?
The sum of the two different names could be the same.
Why would the sum of two different names be the same?
Only the order is different.
Only if the order is different, right? And that happens for many, many different words. Okay, not maybe for names so much, but many words in the English dictionary would be, you know, would be obtained from the same letters. Right? And if two of the if you have two words such that the letters were same, God and Dog, right? Then just because you are just summing up the ASCII values, they are always going to go to the same location. So you know, such kind of things we definitely have to try and avoid first.
Sir, even if the words are not same, like you A, instead of A there is B and instead of C there is B, so again they will add up to make same.
Yeah. So what you are saying is, even if the words were not the same, but A was replaced by B and N was replaced by M, then even then we would end up with the same. That's right. So again, you know, these are all reasons why this is perhaps not such a great strategy, right? Especially when you are trying to convert strings, character strings, into integer. So one technique that is used in such settings is what's called polynomial accumulation. So you're going to, suppose you have the ASCII, you have a certain string, and A0 is the ASCII code for the first character of the string, and A1 is the ASCII code for the second character, and so on and on, right? Now you are going to think of it as a polynomial whose coefficients are A0, A1 up to An minus 1, right? So this is your polynomial A0 plus A1x, and now you are going to evaluate this polynomial at a certain value of x, right? And that evaluation, that value is going to be the integer corresponding to this string, right? That integer might be from a large range, then we will use the compression map to map it to the table. But first we are looking at the hash code map, wherein we are trying to convert a string or a non-integer data into an integer, and we are looking at this setting where the string we have is this, and we are trying to convert it into integer, right? So evaluate this polynomial at some integer value, and it has been, this is, you know, experimental stuff. So people have looked at and found that if you work with x as 33, 37, 39 or 41 with these values, and if you take, let's say, an English dictionary with about 50,000 words in it, and use this technique to convert your words into integers, then you will get not too many collisions. That at a particular, you will have at most 6 collisions, right? So this is, there is no theory behind it, this has been observed experimentally, right? So this kind of is an, is some experimental study in favor of this kind of a hash code map. Let's now look at some compression maps. So, given an integer, now you have to map it to the small range of your table. Yeah. So, one natural thing would be that this k is your integer and your table is of size, let's say little m. So, just do k mod m. K mod m will give you some integer in the range 0 through m minus 1. Yeah. So, k is the key and m is the size of the table. Now, suppose you were to choose your m to be 2 to the something, let's say your table is of size 1024 and you choose your, right. So, m is basically 2 to the 10. Now, what would that imply when I am taking some integer mod 2 to the 10? Then essentially that means that I am taking the last 10 bits of that integer. Yes or no? Yeah. So, think of, write the integer in its binary representation, and then when I am taking mod 2, what does that mean? I am taking the last bit of the integer. If it is 0, then I get 0 always. If it is 1, I get 1. If I am taking mod 4, I am getting the last 2 bits. So, if I am taking, let us say, mod 2 to the 10, then I am getting the last 10 bits. And so, all integers which have the same last 10 bits are going to get mapped to the same location. Now, this is bad, because what we are doing is we are forgetting the other bits of the integer. We are just taking some small set of bits, the last 10 bits, and basing our basing the hash function on that, right. So, one should not do such a thing. You should not take your m in this case. So, if you are using this kind of a compression map, this simple compression map, right, then you should not pick up the size of your hash table to be something like a to be some power of 2. In fact, it helps if you take the size of the hash table to be a prime number. To give you an example, suppose I had 2000 strings that I was trying to put into a hash table. So, I will try to pick the size of my hash table, let us say at 701, which is a prime number, right. This will ensure that if things went off well, then on an average I would see only 3 strings. 701 into 3 is roughly 2000. I would see only 3 strings per location. In my chaining, when I have the linked list, I would have linked list of only length only roughly a 3, right. And one important thing also is that it's also observed that one should not pick your size of the hash table close to a power of 2, because the same kind of effects start happening as when you have the size of the hash table to be exactly a power of 2, right. So, if you are going to be using that kind of a compression map, which is just key mod m, then keep in mind that your m should be something which should definitely not be a power of 2 or even close to a power of 2, and it should preferably be a prime number.
Sir,
Yeah.
it's being not a prime number but being far from a power of 2 power n, that would also work?
That should also work. There is no, so as far as whether it works or not, the problem is that when do things don't work? When you see a lot of collisions happening, right? And a lot of it, as I said, depends upon the data that you have, depends upon the keys that you are trying to insert into your hash table. So, these are generic principles, right, which if you follow will perhaps improve performance, right, but there is nothing here which says that this will not work at all.
No, I mean to say that if we take a number which is not prime, that may even give better performance than a prime number.
Yeah, so there have been instances, or we did some experiment for where if it was sometimes better to take a number which was not necessarily a prime. Okay, what are other kinds of compression maps you can use? So, there is this other compression map you can use. So, essentially I will first read out this second part. What you do is, suppose your keys are in the range 0 through k max. So, recall we are now assuming that our keys are integers, because we first used the hash code map to convert anything that was non-integral into an integer, right. So, our keys are in the range 0 through k max. So, first we convert them from this range into a range 0 through k max times a. So, essentially we multiply each key with a, where a is some number between 0 and 1, right. So first we convert it into this range. Now we take the fractional part of each key. So that corresponds to Ka mod 1. So we take the fractional part of each key. Right? So as a consequence, we get a number between 0 and 1 because we took the fractional part. And now we have to map it into the range 0 through m minus 1. So what can I do? I can just multiply that number I get between 0 and 1 by m. Right? This number was between 0 and 1. So when I multiply it by m, I get some fractional number. So that's why I took this is the floor function, which means round down. So I rounded that number down to the nearest integer. Okay, I'll repeat this. You first took your key, multiplied it by a, where a is some number between 0 and 1. Okay, then from what you got, you took the fractional part of that number, which is again something between 0 and 1, and then you rounded it down. Yeah. So this is another popular compression map. You could have done something different also here. You could have, for instance, said, okay, this gives me, I could just take this and map it to m0 through m minus 1 directly, although it's not clear how you would do it, perhaps divide by m or some such thing, right? So this is one popular way of doing things. And here the choice of m is not critical. Even if m was a power of 2 now, the same kind of a thing that was happening before would not happen, right? Because we have done a lot of jugglery. We have taken that number, first we multiplied it by a, which was some small fraction, and then we took the smaller fractional part, and then we bloated it to the range 0 through m, right? So here it's not critical that m not be a power of 2. So we could use m as 2 to the p. Yeah. And some evidence, there is some evidence that if you use, let's say, a as something like root 5 minus 1 by 2, then it turns out to be good. Okay? So if you use this is called Fibonacci hashing. Okay. Now much of this is experimental without significant theory behind it. So you might want to read up more about hash functions. There is a nice book by Donald Knuth on sorting and searching, which covers hash functions in more detail. There is another technique for a compression map, which is called the multiply, add and divide, which basically means, which says the following: take your key, multiply it by a and add b. Right? What are a and b? A and b are two fixed numbers. And then compute modulo n. N here is the size of your hash table, right? So sometimes I use m and sometimes I use n, but that's the size of your hash table, right? So it's not, so the first technique was just k mod n, but now we are doing something different. We are multiplying it by a and adding b. Okay, here a should not be a multiple of n. If a were a multiple of n, what kind of a problem would you have? A mod n would be 0, so ak mod n would be 0. So this, for any key, you will always get mapped to the same location b. Right? In fact, a and n should not even should be co-prime if possible. Yeah, to avoid any kind of patterns happening. And such a technique is used in your random number generators also. So you might have used the function random, right, as part of your programming, and what random does is it gives you a random number. So if you specify the range, it gives you a random number in that range. So how does it come up with a random number? Right? So many of the random number generators use a technique called linear congruential, are based on this technique called linear congruential generators. What they do is they start with a certain seed. Seed is a starting value which could be obtained, let's say, by taking, which could be user defined. You could provide what the seed is, or it could, for instance, a random number generator could just take the system time at that point or some other information and use that as the seed. And that seed becomes the initial k value. And then you compute this quantity ax plus b mod n, right? And whatever is the value, that becomes your random number. So this will give you a random number in the range 0 through n minus 1. And then for the next random number, you are going to use k, which is the last value you returned. right? Whichever is of last random number generated, you will use that as your value of k and once again compute ak plus b mod n. And then whatever value you get, you will use it for the next time and so on and on. Right? This is how you generate random numbers. So such numbers are actually called pseudo random numbers because they are not truly random. Once you know the seed, you can actually figure out all the numbers that you are getting. There is another technique called universal hashing, which I am not going to go into much detail. I will just briefly tell you what the idea is. So in all of these, so for any kind of hash function you choose, so I suppose I pick up a hash function and I tell you what the hash function is. You can always come up with a set of keys such that all those keys will get mapped to, using my hash function, will get mapped to a very few locations, right? So I think of you as an adversary who's trying to make life difficult for me, let's say, by picking keys which all get mapped to very few locations in the hash table, so that I have to spend a lot of time doing insertion and deletion and searching, right? So what one solution I can employ is that I don't even tell you what hash function I'm going to use, which means that I say I'm going to have a bunch of hash functions, let's say 15 different hash functions, and I'm going to, before the process starts, I'm going to randomly pick one hash function out of these, and then the keys that you give me, I'm going to use this hash function to put the keys into the table, right? Of course, I have to use the same hash function for inserting all my keys, for doing the search, for doing the deletion and so on, right? So for one run of the hash table implementation, I have to use the same hash function. I can't change the hash function midway, right? But next time I invoke this program, I could perhaps use a different hash function because that I have picked up randomly from a set of hash functions, right? So that you as an adversary can never come up with a set of, so even if you came up with a bad set of keys for one of my hash functions, right, maybe that is the hash function I did not pick up at all when I was doing my implementation this time around. Okay, so there are some results which say that you can pick up a collection of hash functions, and such a collection of hash functions is called universal, such that for any two keys the probability that they get mapped to the same location is no more than 1 by m. Okay? So as I said, this was just a very brief idea of what universal hashing is. I am not going to go into detail. When you do your next course on algorithms in the third year, you will see more of universal hashing. So that is as far as hash functions was concerned, right? So we said you use hashing, you will get collisions. There is no way around it. And the one technique we saw in the last class to resolve collisions was what's called chaining, right? If many keys go to the same location, you just chain them up. You just put a linked list there, right? And then you can still do insert, search and delete by doing that operation in that linked list. We are going to see two other techniques today which fall under the general class of open addressing. One of these is called linear probing, the other is called double hashing, and let's see what these are. Any questions till this point? So open addressing differs from chaining in the following key fact. In open addressing, so recall that in chaining, none of the elements were actually stored in the table. They were all stored outside the table. In the table, all we had was a reference to the starting element of the linked list, right? The table was only storing the pointers or the references to the first element of the linked list. But now what we are going to do is we are going to put all the elements into the table itself, right? And we will see how. So as I said, hashing could map two elements to the same location in the table. So we can't put both of the elements at the same location. We still want to put all the elements in the table. So we'll have to find some other location for that element. So clearly, if all elements have to reside in the table, then the number of elements that we are trying to put, n, has to be less than the size of the table, which is m. right? So I'm going to work with m as the size of my table and n is the number of elements that I'm trying to put. Right? This was not a requirement for my chaining technique. I could have the number of elements as larger than the size of the table, because there the elements were not residing in the table, they were residing in these nodes which were connected, which was part of linked list. So each entry of the table is now either going to contain an element or it's going to be null, right? It's going to be null, which means that it doesn't have any element in it. And when we are searching or inserting or deleting, we have to probe the elements of the table in a suitable manner, and I'll come to what this means in a second. Right? So now we are going to think of it as if we are modifying the hash function a little bit. Right? So this U is the universe from which the keys are picked. So our hash function is mapping the keys. So earlier there was not this part was not there. We were mapping the keys to 1 of 0 to m minus 1, right? And that would tell us where this key sits, for instance in the case of chaining, right? Now we are going to say, well, we are going to have a second parameter which specifies key which probe this is. When I am trying to insert a key, I am going to that will be my first probe when I am trying to insert the key, right? I will compute the value of this hash function for that key k comma, let's say 0th probe, so k comma 0. This is the value of the hash function I obtain. Okay, I will look at this location in the table. If this location is occupied, then I have to look again. And when I look again, the next time I will have a value of 1 as the second parameter. The first parameter is still the key k. So I'll now compute the value of the hash function for k comma 1. And this gives me some other location in the hash table. And so on and on. So I'm going to go to different locations in the hash table till I find an empty location if the operation was one of insertion. Right? And depending upon how this hash function is decided will give us many different techniques. So the hash function h is really determining the sequence of slots which are examined for a certain key. Any questions on this?
So U are the is the set of containing the keys.
U, yes, U was the range of the keys. U is the set which specifies the collection of keys that we have.
And so in this we have n less than m.
Here, yes, we also require that the number of keys have to be less than the size of the table. Why is that important? Because we said all the elements, not the number of keys, sorry, I should correct myself, not the number of keys is less than the size of the hash table, but the number of elements we are trying to insert into the hash table should be less than the size of the hash table. Right? If I am trying to insert all the 100 elements, 100 students of this class into a hash table that I create, then clearly the size of the hash table has to be more than 100, because each of the student has to go into one location of the hash table. Okay, so the first technique under open addressing is called linear probing. So what do we do? It's very simple. I have the key k which I am, let's say, trying to insert. I have a hash function h, I compute h of k. This is the first place of the hash table that I look at. If this place, that is table, this place is occupied, if there is some element sitting here, then what do? I just go to the next location. So probe is incremented by 1. And then I once again check if it is occupied. If it is occupied, then I increment again and I go on and on till I find an empty location. At that point, I will put the element k. Right? So this is the guiding principle. If the current location is used, just go to the next location. What is this mod m doing here? To do the wraparound. If you reach the end of the table, then you start at the beginning.
But while retrieving back the keys, we would like to know that how many times we have performed this probe function or which hash function we have used.
So your question is what happens when we retrieve the keys, and we'll come to what happens when we retrieve the keys in a short while, right? But understand this insert first. You are trying to insert, you compute the value of the hash function, you go to a specific location as specified by the hash function for that key, and at that location, if that location is occupied, if there is an element already sitting there, then all you do is go to the next location. If that is occupied, go to the next location. If that is occupied, go to the next location, and so on, till you find an empty location, right? So one advantage this has over chaining is that it uses less memory. Why is that? In chaining, you have to keep track of these references and all, right? Each of your nodes has to have place for the element that it is storing, but it also has to have place for the next, for a reference to the next node. So that kind of space is wasted, all that space is wasted. But this technique might end up being slightly slower than chaining, and we'll see why this happens. So let me show you an example first, and then that will be clear what we are trying to do. So my hash function is k mod 13, very simple hash function. My keys k are integers. I am trying to insert these keys into the table, right? 13 is the size of my table, location 0 to 12. 18, what is 18 mod 13? 5. So 18 goes to location 5, right? No problem. At that point the table was empty, so it can come here, no problem. 41, 41 mod 13 is 2. So 41 goes to location 2, absolutely no problem till now. 22, 22 mod 13 is 9. So 22 goes to location 9, there is no problem here at all. 44, 44 mod 13 is 5. So we want to put 44 at this location, but this location is already occupied by 18. So 44 will now search for the next location. This location is empty, so we put 44 here. Yeah. 59, 59 mod 13 is 7. So 7, we come to this location, it was empty, so we put 59 here. 32, 32 mod 13 is 6, 6 पे 44 है, 44 is sitting at 6. So we go to the next location, 59 is sitting at this location. So we go to the next location, and so we put 32 here. This location is empty still, so we put 32 here. 31, 31 mod 13 is 5. So we should have put 31 here, but this location is occupied with 18. So we go to the next location, which is occupied by 44. So we go to the next location, which is occupied by 59. So we go to the next location, which is occupied by 32 already. So we go to the next location, which is already occupied by 22. So we go to the next location, which is empty, and we put 31 here. 73 mod 13 is 8. So we check for 73 here. This is occupied, this location is occupied, this location is occupied, and so we have to put 73 here at this location. Okay. So very simple idea. All the elements are sitting in the table. So this is the, so now if you just forget the part here, so this is the position of the elements. 41 is at location 2, 18 at location 5, 44 at location 6, and so on. Right? Now this also shows you one problem with this technique. What is happening is that the elements tend to aggregate, form clusters, right? And so you might have to go through many locations while searching for an element. Yes? Okay. So how would one search? Let's see how one would search. So this is the hash, this is our hash table after we inserted those elements. Suppose when we are searching for a key k. So what are we going to do? We are going to compute k mod 13 because that was our hash function. And then this is the first location we go to, and after that if we don't find the element there, what do? We don't say the element is not in the table. Yes, we go to the next location. If at the next location there is some other element present, then we go to the location following it, and so on and on till we either find the element or we reach
Null.
an empty location. If we reach an empty location, then that means the element is not there in the table. Because if the element had been there in the table, it would have been inserted at one of these locations that I had checked. Right? Let's see. Suppose I am searching for 31. 31 mod 13 is 5. So I come here, 31 is not here. So I go to the next location. It's not here either. I go to the next location. Not here either, not here either, not here either, and I found it. When I did not find it here, I can't say it's not there in the location, in the table. It could be there. In fact, it is. Right? So I find it here. Suppose I am searching for 33. 33 mod 13 is 7, so I would start here. Then I come here, it's not here. 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 I come here and I find this location is empty. This means 33 could not be there at all in this table, because if 33 were there in this table, then it would have been, it would have definitely been inserted by this time till this position, because this is an empty location. Everyone with me? So that's an unsuccessful search, and in an unsuccessful search, this is what happens. The search terminates when you reach an empty location. In a successful search, the search will terminate when you find the element. Okay? So that's how you will search. How do you delete? Suppose this was my picture from the previous slide, and now I want to delete 32. So first I will have to search for 32, right? 32 mod 26 is 6, so I come here, it's not here, so I come here, it's not here, I come here, I find 32. So what should I do? Remove 32 from here? Should I remove 32? 32 is found in location 8. Now suppose I just remove it by setting this location to null. I remove 32 from here. Is this a good idea? No. Why not? Why is this not a good idea? Right. Suppose we now search for 31. What's going to happen? 31 mod 13 is 5. So we come here. We didn't find it here. We come here. We didn't find it here. We come here. We didn't find it here. We reach here, and this is an empty location. So we'll say 31 is not there. Well, 31 is there. Why is the problem coming? Because when 31 was inserted, this was a full location. Right? So that's why 31 was inserted later in this thing. But once if you delete this, then you have a problem. Right? So somehow we have to do something different here. We can't just set this location to null. We can't just mark this location empty. Yeah. So lookup will declare the 31 is not present, which is wrong. Everyone with me? So how do we delete now? Instead of setting this location to null, we will place a tombstone, actually an X, right? So a tombstone is just a marker, any marker. You could set a bit at that location, which specifies that this location was occupied by someone, right? And it was not always the case that this was an empty location. At some point this was occupied by someone. Yeah. Now how is this going to help us? When we are doing a lookup and we encounter a tombstone, we don't declare that the search has ended and it's not present. We continue. So as before, if I was searching for 31, I would come to location 31 mod 13 is 5. I would come to this location, go here, see an X here and not null, see a tombstone here, continue till I find either a null location or 31. So I found 31, so I declare 31 is there. So when a lookup encounters a tombstone, it ignores it and continues. When an insert encounters a tombstone, what does it do? It will put the element at that position. Yeah, we have kind of reclaimed this space. Now, one problem with these tombstones is that if there are too many tombstones, right, then what happens? You don't have those elements in the table. Those actually are empty locations, but in your search and all, you still have to go beyond them. Right? So your search, the performance of your search degrades. So what should you do if you have a lot of tombstones? You should perhaps just rehash, just remove all the elements and put them back in again. Okay? The same kind of a technique you do when you have to grow the table. So now you're not growing the table, but you have too many, these markers in the table. So just do a rehash, and that will create empty slots without these tombstones, and your performance will increase again. Any questions till this point? So I'll now come to the other open addressing technique. So we looked at linear probing. Linear probing, we compute the hash function, we look at that location, next location, and so on and on. In double hashing, what we do is we have two hash functions, h1 and h2. h1, the value of h1 gives me the first position where I am going to look for that key k. Okay, and then h2 of k will tell me the offset from the first position where I am going to look again for the key k. Okay, so let's look at this piece of code. So probe is set to h1 of k, so that's the first position I look at, and offset is set to h2 of k. First, I'll just look at the probe, the location specified by probe in the table. If it is occupied, then the next location I'll look at is probe plus offset. Probe is set to probe plus offset, which means this is the next location I look at. Right? If this is also occupied, then the next location I look at is probe plus offset, where whatever, or probe plus offset. Right? So which means that offset is determining with how much distance I am going to advance every time I don't see the element that I am searching for. Right? So if you look at linear probing, for linear probing your offset was always a 1. Right? You were always just going to the next location. So that corresponds to an offset of a 1. If I went, instead of to the next location, I went to always jump one location ahead, as in jump 2 locations, so then offset would have been 2, and so on. So offset, and this offset in this case is determined by this hash function h2. So this offset could be different for different keys. Yeah? Okay, so we'll look at we'll soon see an example of how double hashing works. If m is a prime, then this technique will ensure that we look at all the locations of the table. So in linear probing, because the offset was 1, we would look at all the locations in the table. If there was an empty location, we would always be able to insert the element. Right? Now, we would not like that the following happens, that there are empty locations in the table, but you start from a certain location and then you go, let's say 3 units, offset is 3, so you go 3 units ahead, and then you go 3 units ahead, and you go 3 units ahead, and you keep finding everything is full, and then you come back to the starting location, because then you were not going to be able to insert the element at all, because maybe all of these elements that you looked at were all full, but the other elements in the table, the other locations in the table were empty. So you somehow want that you don't cycle back. But when will you cycle back? When your offset divides the size of the table. So if the size of your table was a prime number, then your offset would never divide it, and so you would this kind of a thing would never happen. In fact, you would look at all the elements of the table then. So this is a small fact you can go back and prove, that if m is prime, then I've given you the rough argument for why this is the case, but you can also prove it more formally. This has some of the same advantages and disadvantages as linear probing. One, it distributes keys more uniformly because now you don't form those clusters anymore. Those clusters were getting formed because you were just going one step at a time. Now, if for some key you are going maybe 7 steps ahead, and for some other key you are going 13 steps ahead, some other key you are going 2 steps ahead, then these clusters are not getting formed anymore, right? And that makes the performance better. So we'll see an example. Okay, I have two hash functions h1 and h2. h1 is the same as before, k mod 13. The elements are also the same as before. We have a table of size 13. h2k is my second hash function and is 8 minus k mod 8. Yeah, so it will always be a number between 1 and no, it cannot be 0 because k mod 8 lies between 0 and 7. So it is between 1 and 8. 0 does not make any sense, right? If it is 0, then we are in trouble. If h2k is 0 for some k, then that means that you are continuing looking at the same place, and if that place were occupied, then you cannot insert the element at all. Okay, so let's insert the first element, 18. 18 mod 13 is 5. So it will go to location 5. Yeah. 41 mod 13 is 2, so it goes to location 2. 22 mod 13 is 9, goes to location 9. 44 mod 13 is 5. So it tries to go to location 5, but location 5 is already occupied. Yeah. So now we have to compute h2 of 44. What is h2 of 44? 8 minus 44 mod 8. 44 mod 8 is 4. So 8 minus 4 is 4. So I have to go 4 steps ahead. So I'll go to location 9. Yeah. But that's also occupied. So I'll go to location 0. That's empty. So our 44 will go to location 0. 59 mod 13 is 7. So 59 would go to location 7. 32 mod 13 is 6. So 32 would go to location 6. 31 mod 13 is 5. So we go to location 5. Now that's occupied. So I compute h2 of 31. h2 of 31 is 31 mod 8 is 7. So 8 minus 7 is 1. So 31 will now go to, we'll check 6. 6 is also occupied. So we'll have to go to 7. 7 is also occupied. Go to 8. And this is not occupied, so 31 goes to 8. 73 mod 13 is 8. So it will try to go to 8. That's occupied. So we compute h2 of 73. 73 mod 8 is 1. So h2 of 73 is 7. So we will go to 8 plus 7, 15. 15 is 2 mod 13. So we go to location 2. That's occupied. So 2 plus 7, 9. That's also occupied. 9 plus 7, 16. 16 mod 13 is 3. So it goes to this location which is unoccupied. So it ends up here. Okay? So this is how the elements would be distributed in the table. Is this clear to everyone? So now we will do some analysis of this technique of double hashing. So recall I am going to assume that the load factor is less than 1. What was the load factor? The number of elements divided by the size of the hash table, n by n. That is less than 1. I need it to be less than 1, otherwise more than 1 does not make any sense. We are talking of a scheme where all the elements have to sit inside the hash table. Okay, and now we are also going to assume, so this is similar to the assumption that we made in the last class, that every time I probe, I actually look at a random element in the hash table, uniformly random. So the first time I probe, I will take a random element, random location in the hash table, sorry, and put the element there, try to put the element there. If it is occupied, then what do? Once again, I'll pick a random location in the hash table and try to put it there. And if that is also occupied, I'll once again pick a random location in the hash table and try to put the element there. And let's see how this performs, because we'll only be able to analyze such a scheme because the other schemes are too dependent upon the hash function that we are using, right? And we might not be able to analyze that. So if alpha is the load factor of the table, then that means that 1 minus alpha fraction of the table is empty, right? If alpha is half, that means the number of elements divided by the size of the table is half, which means only half the table is occupied, so half the table is empty. So 1 minus alpha fraction of the table is empty. If 1 minus alpha fraction of the table is empty, then suppose my search was an unsuccessful search. What does an unsuccessful search mean? That the element is not in the table. When does an unsuccessful search stop? When I get an empty location. So before, how many probes will be required before I get to an empty location? Right? So 1 minus alpha fraction of the table is empty. So let's say 1/10 of the table is empty. Yeah, 90% of a table is full, and 1/10 of it is 10% of it is empty. So expected number of probes required before I hit one of those 10 locations, 1/10 fraction of the table which is empty would be roughly 10. Yeah, because the first time I will maybe with 9/10 probability I will get to an occupied location, and so on and on. So roughly after 10 trials I will hit a empty location because only 1/10 of the table is empty. So if 1 minus alpha fraction of the table is empty, then roughly 1 over 1 in an expected sense 1 over 1 minus alpha probes are required before I hit an empty location and declare it to be an unsuccessful search. Yeah. So this is the expected number of probes required for an unsuccessful search. Okay, let's look at a successful search now. Right? Now here I am going to talk about the average number of probes required for a successful search. Not for one particular search, but if I were to look at all the successful searches. So what are successful searches? Successful searches are searches corresponding to the elements in the table. Yeah, I have some number of elements in the table. Let's say I search for one of the first element. Then how many probes are required? Suppose I search for the second element. How many probes are required, and so on and on. And I'll take their average. Right? Let me try and compute this quantity. So if you recall from the last class, the average number of probes required for a successful search is the average number of probes required to insert those elements, right? Because when we were inserting those elements, we were doing essentially the same thing. Yeah, so it's the same as the average number of probes required to insert all these elements, and this is the quantity I'm going to compute. What is the average number of probes required to insert all the elements that I have in the table? So let's see. When I'm inserting an element, I need to find an empty location again. Yeah. Now suppose my table is, I began with an empty table and I am looking at the number of probes required to insert the first m by 2 elements. Right? Size of the table is m. First m by, let's assume m is 100. I'm talking of inserting the first 50 elements. Right? Suppose I've already inserted 48, 49 elements. When I'm trying to insert the 50th element, what is the expected number of probes that are required? Right? Half of the table is empty. So when I try once, I'll maybe hit a full location. Maybe when I try again, in expectation, I'll just need 2 probes to be able to insert this 50th element. For the other first 49 elements, I might on an average even require less. But all I can say for sure is that the average number of probes required for inserting these elements is less than or equal to 2. And how many elements am I inserting? M by 2 elements. So the total number of probes required is less than or equal to m for these on average, for these first m by 2 elements. Okay, when I show you the rest, you will understand why I am doing it this way. Now let's look at, suppose I have already inserted m by 2 elements into my table, and I am now trying to insert the next m by 4 elements into my table. Right? When I am trying to insert the next m by 4 element, just assume that I've already inserted m by 4 minus 1, and I'm now trying to insert this last element. When I'm trying to insert this last element, how much of the table is already full? 3/4 of the table roughly is already full. Yeah, only a quarter of the table is empty, only 1/4 of the table is empty. So on an average, I'm going to require about 4 probes before I get to one of the empty locations. After all, I'm searching for an empty location to put this element in, right? So I need roughly 4 probes. So in fact, so I'm just placing this as an upper bound. I need at most 4 probes to insert all of these m/4 elements. And so the total number of probes required to insert these m/4 elements is m/4 times 4, which is no more than m, right? Similarly, for these next m/8 elements, when I'm trying to insert this last of these m/8 elements, only 1/8 of the table is empty. Yeah, and so on an average, I require about 8 probes before I can get to one of those empty locations. And so for these m/8 elements, I would not have required, for any one of them, I would not have required more than 8 probes. I would have required between 4 and 8 probes for these m/8 elements. Right? Because when I was inserting the first of these m/8 elements, only 3/4 of the table was full, 1/4 of it was empty. Yeah, but I'm just upper bounding it. I'm just saying, let's say no more than 8. Okay, so just let's see what this means. So the total number of probes required to insert m/2 plus m/4 plus m/8 plus so on up to m/2 to the I. What is the total number of probes required? For this, recall from the previous slide, I said m. For this also I said m. For this also I said m. So what is the total required for these guys? M into I, because this is just 2 to the I. This is 2 to the 3, 2 to the 2, right? So each one of them is m. So it's m times I. And the total number of probes required to insert, after I have inserted all of these elements, how many locations are empty in the table? What is the total number of elements in the table now? Okay, after I inserted m/2 elements, what part of the table was empty? What fraction of the table was empty? Half. After I inserted m/2 plus m/4, how much of the table was empty? 1/4. So it's really this last number here. After I inserted this much, how much was empty? 1/8. So after I inserted all of this, how much was empty? 1/2 to the I, which is 2 to the minus I fraction that was empty. Yeah? Okay. So after I've inserted all of these fractions, I have only 1/2 to the I fraction of the table empty, and the total number of probes required to insert these elements is m times I. Right? So number of probes required. Now what do we want? We have a load factor of alpha. We have already inserted enough elements so that the load factor is alpha. When the load factor is alpha, 1 minus alpha fraction of the table is empty. Yeah. So if I have to have 1 minus alpha fraction of the table empty, then how many probes are required? If I have to have 2 to the minus I fraction of the probes of the table empty, then I require m into I probes. What is I? I is basically log of this quantity, minus log of this quantity. So if I need to have 1 minus alpha fraction empty, so I just need minus log of 1 minus alpha times m. These are the number of probes required. Yeah, I've just gone from here to here. If I have 2 to the minus I fraction empty, 2 to the I is minus I is a number smaller than 1. So if this fraction is empty, then to get to this point where only 2 to the minus I fraction was empty, I required m into I probes. So to get to a point where 1 minus alpha fraction was empty, I need so many probes. Yeah. So the average number of probes required, so this was the total number of probes required, so average was just divided by n. M by n was alpha, so or m by n was 1 by alpha, n by m was alpha, so this is this quantity. So we will now be able to capture it into a table, right? So for unsuccessful and successful probes, when we had chaining, it was 1 plus alpha, recall. Right? For probing, for an unsuccessful search, it was 1 over 1 minus alpha, and for a successful search, what I just showed you, it is 1 by alpha times log of 1 over 1 minus alpha. Yeah? And okay, so with that we will stop this discussion on hashing. There is this last slide which shows how this performance is as alpha changes. Yeah, okay.